We define sensitivity and specificity for binary outcomes. When the outcomes are categorical, we can define these terms for a specific category. For example, in the digits example, we can ask for the specificity in the case of correctly predicting a 2 as opposed to some other digit. Now, once we specify a category of interest, then we can talk about positive outcomes, we'll use y equals 1, and negative outcomes, y equals 0. Note that the word positive and negative are not to be interpreted as in the English language. Negative does not necessarily imply bad. For example, in medical testing, a negative test is usually a good outcome. In general, sensitivity is defined as the ability of an algorithm to predict a positive outcome when the actual outcome is positive. Because an algorithm that calls everything positive has perfect sensitivity, this metric on its own is not enough to judge an algorithm. For this reason, we also examine specificity, which is generally defined as the ability of an algorithm to predict a negative when the actual outcome is a negative. We can summarize this in the following way. High sensitivity implies that, in general, y equals 1 will result in y hat being 1, and high specificity implies that y equals 0 implies y hat will be 0. Although we consider this the definition of specificity, another way to think of specificity is by the proportion of positive calls that are actually positive. In this case, high specificity could be viewed as y hat equals 1, implying that y is equal 1. To provide precise definitions, we start by naming the 4 entries of the confusion matrix, like this. Sensitivity is typically quantified by the true positives divided by the sum of true positives plus false negative. In other words, the proportion of actual positives that are called positives. This quantity is referred to as the true positive rate, TPR, or it's sometimes called recall. Specificity is defined as the true negatives divided by the true negatives plus the false positives, or the proportion of negatives that are called negatives. This quantity is also called the true negative rate. However, there's another way of quantifying specificity, which is the true positives divided by the true positives plus false positives, or the proportion of outcomes called positives that are actually positive. This quantity is referred to as the positive predictive value, or PPV, and it's also called precision. Another important summary that can be extracted from the confusion matrix is the prevalence, defined as a proportion of positives. In our sex and height example, when we used overall accuracy, the fact that our prevalence, the proportion of females, was too low turned out to be a problem. Note that unlike the true positive rate and the true negative rate, precision depends on prevalence, since higher prevalence implies you can get higher precision even when guessing. Because the multiple terms we've just defined can be confusing, in the notes we include a table that can help you remember the terms. The table includes a column that shows the definition if we think of the proportions as probabilities. The caret package function confusion matrix computes all these metrics for us once we define which category is considered the positives. The function expects factors as inputs, and the first level is considered the positive outcome. In our example, female is the first level because it comes before males alphabetically. Given this choice, using our new terminology, females are y equals 1 or positives, and males are y equals 0 or negatives. If you type the following code into R, we will see several metrics including accuracy, sensitivity, specificity, and PPV. You can access this directly, for example, like this or like this. In our example, we can see that the high overall accuracy is possible despite relatively low sensitivity. As we hinted at before, the reason this happens is because of low prevalence. It's only 23%. The proportion of females is low. Because prevalence is low, Failing to predict actual females as females, low sensitivity, does not lower the accuracy as much as failing to predict actual males as males, low specificity. This is an example of why it is important to examine sensitivity and specificity and not just accuracy. Before applying this algorithm to general datasets, we need to ask ourselves if prevalence will be the same in new datasets out in the wild.